When you are working with containerized applications, especially in a dynamic cloud environment, you need a smart way to organize and manage them. How do you ensure that closely related containers can share resources and work together seamlessly, all while being easily scalable and resilient? In Kubernetes architecture, a pod is the smallest, most fundamental deployable unit you can create and manage. Think of it as a single instance of an application or a small group of tightly coupled applications that always run together on the same node. The core reason pods exist is to provide a higher level of abstraction than a simple container. Kubernetes does not directly operate on individual containers. Instead, it schedules and manages pods. A pod encapsulates one or more application containers, shared storage volumes, unique network internet protocol addresses, and options that govern how the containers should run. This abstraction allows containers that are meant to function as a single logical service to be co-located, co-scheduled, and run in a shared context. For example, consider a web server application. You might have the main application container and then a separate container that logs its activities or processes files. Instead of running these as two independent containers that might end up on different machines, you group them into a single pod. This means they automatically share the same network namespace and can communicate with each other easily via localhost, just like processes on a single traditional server. They can also share file system volumes, making data exchange straightforward. To create a pod, you typically define its desired state using a declarative configuration file, often written in YAML. You specify the container images, resource requests, and any shared volumes. While you can create pods directly, in practice, most pods are managed by higher-level controllers like deployments or stateful sets. These controllers handle scaling, self-healing, and updates for your pods, ensuring your applications remain available and performant. It is important to remember that pods are inherently ephemeral. If a pod fails or its node crashes, Kubernetes will automatically create a brand new pod to replace it, rather than trying to restart the old one. This immutability is a key tenet of cloud-native design, promoting resilience and consistency. Furthermore, some advanced patterns like init containers allow you to run setup tasks that must complete before your main application containers start, ensuring dependencies are met. Ultimately, the pod abstraction simplifies the management of complex, multi-container applications within Kubernetes. By grouping tightly coupled components, providing a shared context, and being designed for ephemeral lifecycles, pods empower you to build highly available, scalable, and robust cloud-native systems with greater ease and efficiency. They are the essential building blocks for deploying and operating your containerized workloads.